Hello learners, in continuation to my previous lectures on state variable analysis, few more concepts related to state variable are discussed in this lecture. The first thing is eigenvalues and eigenvectors and how can we determine the eigenvalue and eigenvectors from the state variable model. So eigenvalues are what? These are the roots of the characteristic equation, and roots of the characteristic equation play a very important role in the control system, as the location of these roots simply decides the stability of the system. In case all roots of the characteristic equation are lying in the left half of the S-plane, then the system is stable, otherwise it is not. So it means that eigenvalues are very important to be determined. So they are having certain properties associated with it. Any square matrix A and its transpose have the same eigenvalues. Sum of eigenvalues of any matrix A is equal to trace of the matrix A. Product of the eigenvalues of any matrix A is equal to determinant of the matrix A. And if we multiply a scalar quantity to the matrix A, then the eigenvalues also get multiplied by the same value. If we inverse the given matrix A, then eigenvalues are also inversed. And if all the elements of a matrix are real, then the eigenvalue corresponding to that matrix are either real or exist in complex conjugate pair. Because eigenvalues are the roots of the characteristic equation, so it's very important to determine these values. Then we are having the eigenvector. Any non-zero vector M that satisfies the matrix equation lambda I minus A into Mi equal to 0 is called the eigenvector associated with the eigenvalue lambda I. So with each lambda, for each eigenvalue, there is a eigenvector associated that is determined from this relationship. The eigenvector may also be obtained by taking cofactors of the matrix lambda I minus A along any row and transposing that row of cofactors. So this is about the, here A is what? A is the matrix that we are having in the state variable. So from the state variable model, we can determine the eigenvalues and the eigenvector. Then the second thing is the similarity transformation. The similarity transformation can be described as like we are having the n eigenvectors corresponding to the n eigenvalues that we have already discussed. Then m is equal to m1 up m2 up to mn. It is called the diagonalizing or model or matrix of A. So for diagonalization, we are using m is the diagonalizing matrix, and if we use m inverse into A into m, then the resultant A that will get, it will be a diagonal matrix. So similarity transformation is a transformation that changes the vector A into a diagonal matrix so as to get the ease to analyze the state variable model of the system. So this is the similarity transformation. Then state transition matrix and the zero state response. So let us consider a system x dot is equal to axt plus but, that is the state equation of the system. If we take up its Laplace transform, it can be written as, because in the case of the transfer function model, the main difficulty was what? That we were ignoring the initial condition, but these initial condition cannot be ignored in the case of the state variable modeling. So here we are taking into account then. So x dot is equal to axt plus but. Then we take up the Laplace transform on both the sides. We get sxs minus x naught is equal to axs plus bus. Then we keep xs on one side. Then we'll get xs as equal to this from this equation. Then we just, as we had said, si minus Laplace inverse of si minus a inverse, that is equal to the state transition matrix. So if we just take up its inverse Laplace transform, then x's its inverse Laplace transform will be xt. Laplace inverse of si minus a inverse is equal to theta t, that is the state transition matrix, x naught as it is. Then Laplace inverse of si minus a inverse into b into us. So this expression, it is theta t. We have written theta t over here. In some of the books, you'll find phi t over here. So this is equal to xt is equal to phi naught, phi t x naught. There are certain properties of the state transition matrix. So theta naught is equal to 1, and theta of minus t is equal to theta t to the power minus 1. Theta t to the power n is equal to theta nt. That you can simply get from the expression that state transition matrix can also be written as equal to Laplace inverse of Si minus A inverse. This is also equal to e to the power at. So when you substitute t equal to 0, it will become equal to 1. When you substitute t equal to minus t, it will become phi t of inverse. And if you substitute here, this is to the power n, you'll get this expression also. Then a very important aspect of the control system is controllability and observability. Controllability means that the system is controller. A control system is said to be completely state controllable if it is possible to transfer the system state from any initial state to any desired state in specified finite time by a control vector ut. That is the definition for controllability. That we can take up the system to any desired state in a finite time interval. And how do we decide the controllability of the system? That can also be ascertained with the help of the state variable model. So we just consider the state equation of the system. X dot t is equal to axt plus but. So from here we can identify the matrices A and B, and then we define a composite matrix QC, that is B. Then we write AB up to, we'll just keep on increasing the power of A up to an minus 1 into B. So if the rank of the matrix QC that is such formed is n, then the system is said to be controllable. So in order to ascertain the controllability of a system, it can be easily ascertained in case we know the state variable model of the system. Then second thing is about observability. A system is said to be completely observable if any state can be identified by measurement of the output over a finite time interval. So Kalman test for this is, we just take up the state variable model. X dot t is equal to axt plus but. Output equation is yt is equal to cxt plus dut. This the system corresponding to this state variable model is completely observable if the rank of the observability matrix is n, and observability matrix is formed as C transpose, then we'll write down A transpose, C transpose, then we'll keep on increasing the value of A up to A transpose to the power n minus 1, C transpose. When we write the observability matrix and its rank comes out to be n, then the system is observable. If it is not so, then the system will not be observable. So from this this brief video, you have come to know that from the state variable model, we can easily get the value of the eigenvalues and eigenvectors, which help in deciding the stability of the system. Then the second thing is that we can get the we can have the condition for the controllability and observability of the system that help us to ascertain that whether the system is controllable or observable or not. That also we can get by the knowledge of matrices A, B, and C by using the Kalman test, as has been indicated within this video. Then the other thing is that once we are having the state variable model, then how do we get the solution of the state? So that can be determined with the help of the state transition matrix. So that we have also defined with the help of the state transition matrix, which is a very important matrix from the point of view of the solution of the state variable model. So with this, the brief lecture on the state variable model I just want to conclude it over here. And in the next lecture, I'll be starting with a new topic. Thank you so much.